So good afternoon, ladies and gentlemen, and thank you for tuning in to another Risk Institute online session. Today, we're especially fortunate to have with us Professor Kok-Kwang Phoon, who will talk to us about his research in mapping site investigation data in data-centric geotechnics. So the presentation will be around 45 minutes and 20 minutes of questions and answers. So please, could you make sure that your mics are muted, and if you have any questions, either leave them in the chat or select them on behalf of Professor Phoon. But first, I'd like to make a few announcements. So the next three talks that we have scheduled are the governance of systemic risks, which will be next week by Dr. Pia Johanna Schweizer. Following that, we won't have any talks until January. So our next talk will be 5th of January with Dr. Georg Schollmeyer. And then the 18th of January, we have Miss Peg Coleman. Finally, we have the Risk Institute annual showcase on the 1st of February. So if you'd like to put that in your diaries, and if you'd like to participate, just send me an email and I would love to put you into the agenda. So just a quick introduction. Professor Kok-Kwang Phoon is Sheng Sang Man Chair Professor and Provost in Singapore University of Technology and Design. He obtained his BEng and MEng from the National University of Singapore and his PhD from Cornell University. He is particularly interested in developing statistical and other data-driven methods to support decision-making in geotechnical engineering, which you'll hear more about. And he has edited 3 books and authored 1 book, Model Uncertainties in Foundation Design. He was bestowed the ASCE Norman Medal twice in 2005 and 2020, and the Humboldt Research Award in 2017, among many others. He is the founding editor of GeoRisk, appointed board member of the ISS-MGE and advisory board member for the WEF Global Risks Report. He was also elected as a fellow of the Academy of Engineering Singapore in 2012. So he has a lot of achievements and I'm really excited to hear his talk. So let's give a warm welcome to Professor Kok-Kwang Phoon. If you'd like to start sharing your slides.
Thank you very much, Francis. Let me share my slides.
Oh, apologies, let me stop sharing.
Is this turning out okay?
That's perfect. If you'd just like to full screen, I think that would be ideal. Yeah,
all right, let me
great.
do that. So a very good afternoon to all of you again. It's good evening in Singapore. I hope everybody is doing well. But certainly, thank you very much for having me and the really generous introduction from Francis. I wanted to talk a little bit about doing a mapping of site investigation data. So this is something that I guess everybody could understand. Is a core function in geotechnical engineering. And to introduce the topic for those of you who may not have been working in this area, I wanted to share with you this very beautiful picture. I took it from Tim, my good friend from Tampere University in Finland. So this represents one of what we call cone penetration test rig, right in the middle of the Finnish winter. So a cone penetration test is just simply equipment where you basically penetrates a cone into the ground, and by the resistance encountered, you get some kind of information about the ground. The ground that we're really interested in, I'll talk about that, the size of the ground. The size of the test we are talking about at this point in time, the area of the cone, the cross-sectional area of the cone will be something maybe the size of a quarter. So it's pretty small, but this is a nice picture. Just to give you a sense that, where the data is coming from and, how much data you're going to get in our area. And this is a very important point as I continue in my lecture. So first of all, let me thank Scott. Thank you very much, Scott and Francis, for inviting me to give a talk. And I'd like to thank Professor Chin from National Taiwan University. So it's a close collaborator of mine. There's no need to take any notes because we have published a paper on this talk, and you could download it for free if you wish to know more about what I'm talking about. So maybe as an introduction, I could share with you a survey that was conducted by the ISSMG. That's the International Society of Soil Mechanics and Geotechnical Engineering. There's only one international society in our area, and so it encompasses everybody. And this is the only survey we've done on this topic of machine learning in geotechnics. There's a lot of questions, but I thought I'll just share out of interest 3 questions. So one question we did ask the participants whether they think, all these digital tools and digital technology will impact us. And I think overwhelmingly, if you look at the stats, more than 75% or 80% thinks that it's very likely, or likely to very likely in a decade. And another interesting question is to find out where do they think what do they think will be the application that will be affected within a decade? And the majority selected site characterization. That's not surprising because that's like you could say that's our bread and butter, understanding the ground. So it's not really surprising. And that's the topic of my presentation this evening. Just to give you a sense of the demographics, the majority of the people that responded to this survey are basically what we would call the young engineers. So I think they are really excited about some of these changes that will bring into our profession. Certainly, I'm not the only one talking about it, so I just want to get the record right. If you guys were to download the State of the Nation report and this ICE, so they already published a report on digital transformation in 2017. That applies to the whole civil engineering, not just geotechnical engineering. If you do check out their website, it's all about what you could do with data-driven technology. So this is something that's very widely spoken about. I think in terms of geotechnical engineering, the question that I encountered most is that people start asking me in what way we could do anything about it, right? Besides talking about it, in what way could we do research in this area, and what are the relevant questions? And I thought that this is something of interest to all of you. So I wrote a very interesting article about 3 years ago. Actually, I did that when I was spending time in Leibniz University. That was the last time I left Singapore because that was part of the Hamburg Research Award. And I wrote this interesting article about the Goldilocks dilemma, which I'll explain in about 10 minutes. So you bear with me, that is really important because the first thing we got to understand, and in any areas that we work in, we have to understand the data. So I have a very simple thinking. The way I think about data is very simple. To me, the very best kind of data, you can think about it as a God-sent data, and God-sent means that the data is your answer. So that must be one extreme because you don't even need to make decision. You get your answer. The other extreme, I call it bad data. So an example of bad data would be things that are fake. So I just sit down and I cook up the information. It has no bearing to reality. I put that the other extreme. And one way you can define bad data will be a case where it's worse than no data. So because it misleads you, right? Since it's fake, you'll be making decision that is wrong. So if you have no data, at least you could just rely on your experience. So I would classify bad data to be on the left of no data. And of course, geotechnical engineers, if you have worked with us, our holy grail is to look for good data. So these are basically very high quality information. You do careful testing, careful sampling, undisturbed sampling. You get the information, you do careful testing in the lab. And if you could get the information that fits the model, the physical model that you're using, then that would be our ideal version of what kind of data we wish to collect. Yeah, of course, in between good no data and bad data, I call this data ugly. They are basically data that you have, and this is something that is on our table, on our hard disk. This is the kind of data that you get if you run a site investigation program. And I'll talk a lot about it for a very simple reason. This is just a table to show you what kind of real world data we have. The columns represents the different test type, which I will not explain. And the rows represents the depth in which you collect information. Sometimes you may have more than one of this table because you test in more than one location. But this is good enough for you to understand physically, very clearly in very concrete terms, what kind of data we are dealing with in geotechnical engineering. The reason why I look at all this classification, if you recall, is that we are trying to ask ourselves question, how do we put our hands into this idea about data-driven method? And we want to think about data. And the first thing we need to think about is that you need some amount of information. And so among the categories that I basically presented, the only category that we have a lot is basically the data that we have by definition. The good data that we aspire to get, we hope to get, these are really, really kind of like small number, very limited. In fact, because of this circular reasoning, right, the profession keeps looking for very good data. And because good data is limited, the profession keep arguing that because data is limited, there's nothing we can do with any data-driven method. So we basically took an opposing view that why don't we look at the data that we have a fair amount of, and we ask ourselves the research question, what we can do about it. Maybe we can't do much about it, that's fine. But that's a valid research question. I don't really know how much bad data we have, right? That's another research question. So why did I write the article about the Goldilocks dilemma? And that's just my own current hypothesis. Again, it's based on the amount of information that we have. My hypothesis is that if all you have is just very, very small amount of information, let's say you have 2-3 pieces of high quality information, the tool that we have now, which is basically physics, is actually an extremely powerful tool, right? So this is one of the less well-emphasized aspect of physical modeling. So with only a few key pieces of relevant information, you can do a huge amount of really wonderful prediction. I'm not sure what else you can do, like if you only have 2-3 pieces of information. In fact, you look at the so-called the standard model for physics, they only have a couple of parameters, and they could basically simulate the entire reality. I've just threw out a number like 1,000, but maybe it could be 10,000, it could be 100,000. So you have enough information, you have lots of it. You could think about using all these standard machine learning tools that is developed in other areas. But my hypothesis is that you need a lot of data. I think the issue we face in geotechnical engineering is that we're in this, what I call the intertidal zone of this data ocean. We are intertidal because we are not a lot. We are not very little. If we're willing to accept what I said about ugly data, if you are in this intermediate intertidal zone, you need to consider Bayesian because uncertainty is important. You can't make absolute kind of assessment. And so I'm just targeting that if you want to work in this area, you got to work in Bayesian machine learning. And you got to think about how to combine small and big information. I'll talk about it. This idea about small and big data is very important in our area. So that gives you a very quick sense of how we analyze the information that we have, the attributes. And then based on this, we start asking ourselves what we can do about such information. What will be our target, and we haven't achieved that. I kind of put it out in big fonts. The target is definitely, in my opinion, for data-driven methods in geotechnical engineering. You have to use real data. And you have to use real data to help to make real decision, and the real decision will belong to a real project at a specific site. If I consider that to be my objective, then physics will not work because physics is about generalization. Physics cannot give you what I call a highly personalized or highly customized version of what you should do at a particular site. This is something that I guess data-driven methods are really powerful. So we are now exploring the space of a data-centric geotechnics, and we ask ourselves if we are interested to bring value to geotechnical engineering, thinking along the line that is based on data. Then what kind of principles should we follow? We work out 3 principles. The first principle is very obvious. Data centricity simply means that from now on, our research agenda is that we are going to think about what kind of methods we can develop to make sense of actual data. We're not going to think the reverse, where we have a method and there's the responsibility of the user to go and figure out how to collect the kind of good quality data to fit my method. I think that will not that will not allow us to progress. So we are thinking that way, just simply because we want to make headway in all this data-driven method. I don't think you can do any of this work in abstract. In other words, you can't just simply import methods that works elsewhere and simply things that you work in the geotechnical context. And I spoke a little bit about ugly data. I'll talk a lot more about that. I need to talk about the fact that every site is different. So there's one example of geotechnical context. Because the ground condition you encounter, they are not manufactured. So there is this very important item of a site specificity that we need to consider. And finally, we have to be very, very mindful that this is not a theoretical exercise. Else you're not going to convince the practitioner to come on board. And so whatever we do has to show value. And it has to show value not in a generic way, as I kept saying. It's a specific site, specific project. This is very, very challenging. It has something to do with the scale of the site that we are talking about versus the amount of information that we have. The scale, I'll talk about it, but I think all of you could immediately relate that the site has to be 3D. So immediately, the agenda that we started off from, we don't do 1D, we don't do 2D, because it just violates the reality that we want to work in. So these are three things that will be guiding our research that we've been doing for the past 5 years. One of the topic, as I've said, within data-centric geotechnics that is kind of a low-hanging fruit is this idea about site characterization. And so the rule of the game that we impose on ourselves would be that this would be a methodology where you could rely on what you measure at the site. Remember, you have a specific site, you get data from there. But since you're interested in data, we start asking ourselves, what about data collected from elsewhere? Other projects, past stages of the same projects, neighboring sites. Broadly speaking, you can define a data to be anything, right? Don't have to be numerical, or we haven't got that far. So we're working on numerical data. And our research question is to look at data from routine projects. So again, that's the rule of the game. You can't select the site and say that, hey, I'm interested in this site because I got lots of data. The question is that will your method apply to any routine projects? So that is important, all right? And the data is small for most of these projects that we are aware of. You can also get data from similar projects. I'll show you examples later. We call them big indirect data, just to be emphasizing the fact that this data cannot be applied directly to your site due to this nature of the fact that we have site differences. And then what we try to do now is to develop what we call a quasi-site-specific model. And this model, we hope that it can be trained by both big and small. And I'll talk about that subsequently. And then finally, of course, your method has to be computable in true scale, 3D. This whole thing is just an aspiration at this point in time. We did not fully solve this problem. So as not to disappoint you, but we did make some headway. And that's exciting, despite the fact that I actually thought we're not going to make any headway. So maybe let me start with the site itself, thinking about what the site should be like. And the easiest way is to look at a footprint of a building, and I just simply select perhaps a very famous building, Empire State Building. I found this really nice old diagram, drawing a plan view of the Empire State Building, not the ground floor, by the way. That's on the 21st or 24th floor. But if you look at roughly the dimensions, these are basically in foot and inches. So you'll realize that maybe this is like 235 foot, right? And that translates to something like, well, of the order of about 80 meters or so. And the width is about 164 foot, and that translates to something like maybe 50 meters or so. It doesn't matter what's the precise number. I want you to get a sense that even just within the footprint of the Empire State Building, you want to build foundations, you want to build excavations to support this building. There will be roughly the size, the plan view of the ground that you must have some knowledge of. I didn't talk about the depth dimension, but it's enough to think about the plan view, roughly of the order of 50 by 100 meter, maybe, if we're not too picky about it. So I hope you will think about that. And again, the subsequent presentation I'm going to make is all about challenges more than solution. And we have actually published these particular challenges this the early part of the year. And you may not be able to download it, but you could email me, and I would be able to share the paper with you. But if I could, without reading the paper, we basically postulated 3 challenges. One is that we try to make sense of what is exactly this ugly data that I've been talking about. So now we need to be specific, we need to be concrete. I want to talk a little bit about site recognition. That's a very important key problem, or even a core problem in geotechnical engineering. And the third thing I may not have time to talk about is stratification, because that's a natural state of the geological deposit that constitute your natural site conditions. So if I could, I'll spend perhaps the next maybe 10 minutes each to go through ugly data and to go through site recognition. So that's how I'll organize myself going forward. So again, I thought it's really easy if I just show examples of what is a site, although you have a sense from the Empire State Building. I'm basically looking at real sites now in the city of Shanghai, which is very big. You look at the scale, this is a 10-kilometer scale. So this is certainly, the city of Shanghai is certainly larger than Singapore, just to let you all know. Singapore only measures something like 40 kilometers east-west, and maybe 20 odd kilometers north-south. So you could basically fit the whole country of Singapore into Shanghai boundaries. What we did was that we collected data from a subway project. In each of these projects, which I'm showing on the right, if you look at the scale is about 100, 150 versus 50 meters wide. So again, it's not too different from the Empire State Building. And basically the dots, the squares, the dots, the stars represents the different kind of tests that you conduct. And so you do a handful, right? Less than 10, I can safely say. Each of these represents what we call site-specific data. That's all you have, by the way. At this point in time, that's all you have in a routine project. So very clearly with this picture, I hope you from now on, you will just think when you talk about small data, site data, this is the picture. One of it, by the way. I talk about big indirect data. So if you put all the subway information together, and there's a lot, right? Because there's a lot of subway stations, and you could even get site data from other parts of Shanghai, because there's huge amount of construction, and you can just throw them into a database, and that becomes your big indirect data. So I think it's quite a lot, clearly. So now we are zooming into the actual data itself, which I've shown you a table, but this will show you a second table from Metro Line 13. So Metro Line 13, if you recall, Jingsha Station, there will be the site here, the one on the top right-hand corner, all right? And that's the information that you have. There's only one slide, by the way. I don't have pages and pages of this. Again, you see the columns, these are different tests. You see the rows, these are different depth. You see a variety of laboratory and field tests. And you see all these blue empty cells. The reason why I highlight them in blue is that they are missing. The simple reason is that you do not do every test at every depth at every location. You don't do that. So you got all these incompleteness in your table. Those of you who work in this area, I'm sure all of you do. You're beginning to see that the problem is getting more and more difficult. It's not just a question of small sample sizes. It's a question of multivariate, small, and incomplete, among others. So we create a simple acronym to remind ourselves the actual data that we're working on. And we never lose out the fact that all our research is now focused on music 3x. M is for multivariate. So there's no site investigation program that I'm aware of that you only do one test. That's pretty silly. You have a handful, it's not even two. And then I'll talk a little bit about, I'm sure you're aware that because it's a natural site, you'll be uncertain, but I need to explain what is the meaning of uniqueness of our data. And sparse is obvious because we don't collect that much data. We don't have that many tests in the first place. Incomplete, I already mentioned that you don't do every test at every depth at every location. And I spoke about the possible presence of a corrupted or bad information. And we haven't actually done a lot of work on that. So the C is quite missing at this point in time, and I would certainly encourage those who are interested to work in this area. It's pretty challenging in case you're thinking that, hey, Prof, we have solutions. But what you have in classical statistics and outlier analysis is not done under the conditions of music 3x. I don't think there's a solution out there if your data belongs to music 3x. And 3x means 3D spatial variation. Now, that's a natural state. You will never find a piece of ground where there isn't any spatial variation. So that doesn't exist because of the natural formation process of your ground deposit. I promised to talk about uniqueness, and I wanted to show you this. So this is real information. The gray circle dots represents a big database that we collect, by collecting information from all over the world. You get this very big scatter simply because they are very generic, right? And the triangles represents data that we have in Shanghai, not in one site, by the way. This is a couple of sites combined. So if you take one site, the one site would have its own signature, but already this picture is telling you that the uniqueness is not that easy to recognize because the Shanghai data is embedded within our generic database. It's not like isolated. So if you talk about identifying the uniqueness, I'm sure you could start imagining the difficulty of isolating this particular signature of Shanghai, for example. I'm going to talk about ugly data today, but I thought we must all let our imagination run wild because first thing I should say, this is something that I think I learned from Scott, is that there's no such thing as a deterministic data. There isn't. I like the way Scott presented it because I think it's just an arbitrary simplification that for some historical reason we cling on to a single number. Now that number doesn't exist in geotechnical engineering. For the past 50 years, there were a whole bunch of people working on probabilistic techniques, and well, I think there's a fair representation. At least it's not a single number. And I think Scott and some of you would be very much more expert than me in using imprecise kind of representation. I call them even uglier, no offense. And of course, you have interval information and so on and so forth. Information gets less and less, clear, and it gets further and further away from the deterministic representation. So these are numerical data. The wonderful thing about the space that I play in is that we actually have data that's categorical. So these are not even numerical information. And you all may be aware that there'll be ordinal and nominal information. Ordinal has basically information that you could rank. Incidentally, these are not invented by me. These data are not invented by me so as to give all the students nightmare and to make your life very, very difficult. This information, by the way, is the information you work in rock engineering. So rock engineering is worse than geotechnical engineering, which focuses on soil. I give you one example of what we call a geological strength index. This is an index to measure the so-called strength of the rock mass, and it's a function of you don't really know what this number means, but it's a function of what we call the Blockiness Index. And you look at the picture, right? The Blockiness Index is just a way of qualitatively categorizing how many of this fracture you have in a rock mass. If it's very intact, it's the best. It could be totally disintegrated, so that would be very poor and very weak, right? And the engineers thought that it's good enough to divide into 5 blocks. My apologies. And so the ranking between the blocks makes sense, but the number itself has no sense, right? You can call them 1, 2, 3, 4, 5. You can call them 2, 4, 6, 8, 10. You're beginning to see that numbers don't make sense, but I can say that the rank 2, let's say blocky is rank 2. I can say that rank 2 has is more intact than rank 5, which is disintegrated. This is almost a green field. No one is looking into it, and we hope to look into it pretty soon. So this just to make sure that we understood that my ugly data is not exactly the ugliest. It's not exactly the ugliest candidate in the whole set of data that we have to grapple with in soil and rock engineering. So I spoke a little bit about site-specific data, but let me talk about big indirect data. And these are really useful. So people have been collecting all this information, including ourselves, for the past 10 years. And actually, there are lots of this out there in national databases. I think you all should think of ways of collecting and sharing this information because they're going to be very useful. Let me explain at the end of my lecture why they're very useful. But the first thing is to convince everybody that the database exists. So it's not like we are talking in hypothetical terms. We have the largest we have collected for clay will be this database that I'll be using subsequently in my analysis. It consists of about 7,490 records. That's a lot. As you could see, for small data, we have something like 10. So 7,000 is a lot by our kind of measurements. And it is a multivariate database, defined by 10 different kind of soil parameters. But I won't talk about that. Just to convince all of you that we have data from not just all over the world, we have data restricted to regions and of course different kind of soil parameters. Recently, over the past 3-4 years, in fact, the last paper we did was last year, we start collecting rock mass information. So therefore, as I've said, we are gradually moving towards a rock because it's important and no one is working in it. So why not, right? A wonderful research problem. We have actually published books on all these databases. If you're interested, so all these are available. It's nicely written up in a digested form if you need to make reference. Incidentally, in geotechnical engineering, you don't just basically conduct tests just to know what is the ground condition. You actually conduct tests on the physical geotechnical structure. Of course, the most common would be foundations. You have foundations under all buildings, except the really old ones. I'd like to show you one of the biggest tests we did in Singapore, because we did it below this Marina Bay Sands. You all may know this is a very famous hotel with a bridge structure at the top of the building. There are actually 3 of them. On top is actually a bridge. And on top of that, of course, if you ever have come to Singapore, there's a nice swimming pool. You would pay just about 10 Singapore dollars and get yourself up there, buy yourself a drink, and maybe take a dip in this wonderful swimming pool that oversee the Bay Area in Singapore. So this data is expensive. You could see that the idea is to jack the to put in a jack against the surcharge. The surcharge are these concrete blocks, right? And then by jacking against it, you exert a force on the test pile. Expensive. You do that almost every site, maybe not a lot, but then these are expensive and valuable data. So they exist, but they are even more sparse. We have also collected lots of database. So these are another source of big indirect data. So I won't go through it, but just to let you know that in this case, having database of the size of 900,000 is actually very, very big, because these are load tests. These are not soil data. And we got a book published last year. So all these databases and how they should be used is now available. So the book came out at the beginning of this year. Although we were working on it for the whole of last year, I'm always explaining to many of my colleagues, right? If you're ever locked out of your labs, if you're ever locked out of your office, and you're wondering, twiddling your thumb, wondering what you should do, then why do you write a book, right? I mean, that's the best time, writing a book when you're working from home. Incidentally, this is not the only data. So if you need real data to play, remember the data-centric geotechnics, you need real data. If you need real data to play, you can go to our website, and there are lots of people sharing data. So we've created a database sharing initiative. You could just download your favorite data and start playing with it. So I think that will help our research, I believe. So very briefly, I took up 10 minutes on the ugly data part, and if I could, maybe I could move on to the next topic, which is even more interesting. We call it site recognition. So if you're wondering what is site recognition, well, it's like facial recognition. That's how we end up with the word site recognition. The idea is that, yeah, we know that the site is really different, right? I mean, a site in Singapore, for example, is not a site in Bangkok. They're not the same, even though they have a marine clay, for example. So the environment may be the same, but they are not the same. So the idea now is that how do you actually combine small data with large data? Remember, that was my question at the very beginning. And it has something to do with site recognition. I think that is very obvious to all of you, but maybe I can look at it from this perspective again, using back the Shanghai data. The ellipse show the kind of like the scatter of the Shanghai data. As I said, the Shanghai data is not distinct from the generic data. So that's what I meant by the uniqueness is actually kind of difficult. Anyway, you can't distinguish by eye. So that would be my conclusion. You need some clever algorithm to capture the differences. Why do we need to bother ourselves with this? I mean, there are lots of technical reasons, and we have written papers on that, and that's not important. I just give you a simple example using one of the most popular, or most sophisticated tool we do in geotechnical engineering, which is we try to convert a few test result. As I've said, I show you that the nice test rig in Finland. You poke something into the ground, you get some information, but the information is not really what you need for design. So you try to map it to a design parameter, which could be some kind of undrained shear strength. The standard technique now is just simply to collect data from all over the place for material types that look somewhat similar. And then we use our wonderful linear regression. We get a curve and we say, well, that's the recommended procedure to convert your field test to the desired design parameter. So the question, as I've said, we want to ask ourselves whether we can contribute to practice, right? So can we do anything better? Well, the first thing you got to understand is that your information at a single site. So I'm trying to illustrate the single site, right? Like the Shanghai versus the generic database. The orange dot are the so-called what you need at that precise point that you need to do your project. You don't have a lot, that's why I drew 4 dots. You take the most naive approach, which is what we did currently, is just combine orange with red. Pretend that the red dots, they are a lot, let's say 7,000. Your line is not going to move because the red dots will totally overwhelm your orange dots as if they don't exist. So actually you try to throw in information that's very relevant, but it doesn't move the line. Of course, some of you already realize why is it that you need to use a red dot, because you can't draw a regression line on 4 points. The statistical uncertainty is hopeless anyway. So if you talk about site recognition, right? If there's a way among all the red dots, you manage to figure out some way, and I haven't said what way. If you could think of a way, all the red dots, you isolate dots that are closer to the orange dots. Let's assume these are the green dots. I call them similar data. Then you can actually get a new transformation model relating field tests to design parameter that suits your actual site. So it's customized to the actual site. I like this example for one reason. You cannot use physics. There's no physics that allow you to do this transformation. None whatsoever. So by using this example, you're going to play the data-driven game. So that's interesting for us. So that will be the example that I hope to show subsequently. So let me show you how we go about attacking this problem. So now we are down to the research that I've been doing for the past maybe 3 years. So this is something really recent, 3 years. Let me use a set of data that is real. As I said, we always work with real data. So this is a Taipei data. We only have 9 rows with the usual host. But I wanted to point out to you 3 columns that are of interest, because I will show you 3 figures. Of course, these columns are important for design purposes. One of them is this sigma p prime. That is what we call the stress history. We only got 3, by the way, because you need to have undisturbed soil sample, and you need to do it in the lab. And usually you don't do a lot because they are costly. And then you have your undrained shear strength column here. And then the last one, you have plenty because this is your cone test. That was the machine that I just showed you at my cover slide. You just poke something to the ground, you measure the cone tip resistance. You can measure as much as you want, every 2 centimeters actually, to be precise. But in this particular table, look at the number. My n is equal to 3, 6, and 9. So 9 is considered to be a lot. So that's the table I'm working on now for the next few slides. Maybe I start with showing you information that's nothing to do with the site. So this is, remember my big database I collected from all over the world, 7,000. If I plot them in a scatter plot, you get all these blue dots. And the scatter is huge simply because they are all over the world, right? You could actually use this, and engineers are using it, by the way. So it's not like it's not useful. We have a lot of design guides that are based on all these blue dots. The key question, as I said, we talk about value, right? The key question is that you look at the lower bound. This is a 95% confidence lower bound. Let's assume that you use that as a rational way of selecting what we call the cautious value, the conservative value. So the lower the dashed line, the more conservative is your choice of design parameter, or in the case of Eurocode, they call it the characteristics value. The more conservative you have a number, clearly your design becomes more conservative and everything else becomes very costly. So you can do it, but you do it at the expense of money. So can we improve? That was the question that we posed to ourselves. The first thing that we did was that we developed a new way of characterizing the multivariate distribution for the music 3x information that I just shared. And what we did was that we used the Bayesian method that explained. We assume that the mean, so this is multivariate, so you get a mean vector, you get a covariance matrix, and you also get information that are missing. We consider all this to be random. And then we basically, through appropriate choice of the conjugate prior, we just do updating based on whatever data we have. We update the mean vector, the covariance matrix, and the matrix of missing information. We do it iteratively, and eventually we will have the so-called the distribution of mu, c, and xu. I promise not to bore you with more details, so that will be my last 2 slides dealing with mathematics. But what is important is that you using this particular technique, right? Because it's Bayesian, it doesn't matter how much information that you have. So if you have 2 dots, you just end up with a very diffuse, a multivariate distribution. This is not a real information. It's just for illustration. What I did was that I simulated 2 bivariate normal distribution that are independent. So the covariance matrix is identity. The mean is 0. There I just simply apply this technique on it to get the distribution. Of course, you will not get the bivariate with 2 points, right? Notice that my correlation coefficient is a distribution. It's not a single number, simply because all my parameters are distribution under the Bayesian assumption. Of course, you have 10, you start seeing convergence to that bivariate, and you end up with 100, you end up with a nice bivariate. The correlation coefficient starts converging to 0. So it shows that the method is, well, it looks correct, at least mathematically. But you know, you're not going to get 100. So the key idea is to play within this 10 and 2 space. So if you apply that technique to the type A data now, so the red dots are real data now. These are not simulated anymore. You look at the red dot and I apply this particular technique, you end up with simulated gray dots. So these simulated gray dots are like what can happen if I do more tests in type A. Maybe they will scatter around the red dots as shown. We were actually very reassured when we got this result, because you look at it, the way the gray dots are embedded within the blue dots looks somewhat like this. This is real, by the way. This is not simulated. So that's interesting. We got something that looks like this. At least qualitatively, it looks reasonable. And of course, we're not very happy about that. I'll be stopping soon anyway, just to let you all know that we start looking at a Bayesian, hierarchical Bayesian model. I just explained to you what we did for one site, where we basically use the data, we train and we learn the mu and the c. You could do that for different sites, right? And then of course you could now look at the distribution of the mean, you could look at distribution of the covariance. These are very standard techniques in hierarchical Bayesian modeling. We find to be very useful. I mean, physically, the top layer means variation between sites, and the bottom layer means the variation within a single site. We tried this technique again using our generic databases. So this was the blue dots that I showed you just now. You use the hierarchical Bayesian method. Basically, you will learn. You will try to treat each of these sites differently, and you end up with a different distribution. And so now, if you try to perform your inference, right, assuming again the type A data, and I only selected 3 records, what happens is that the hierarchical Bayesian method based on 3 dots. The 3 dots are real, the gray dots are real. None of these data points are simulated. You can actually learn that these surrounding kind of sites looks like the same as your 3 dots. And so by doing that, you will bring information from that big generic database now you're doing it in a discriminate way, by the way, not in an indiscriminate way. If you do that, I think the key thing is that you can actually reduce the gray. The gray is almost as good as the blue, honestly, in terms of scatter. But if you apply the hierarchical Bayesian method, you end up with a much smaller scatter. And as I said, that translates to choice of a lower bound that is a lot less conservative and probably a lot closer to what you have at the site. So this is something we thought very interesting, that we think we're beginning to get some useful information. The key thing is that we're getting information using real data, not artificial data, and also using the constraint of the sample size of real data, like 3 data points. I think that's a bit insane that we're able to get some answer out of it. So we are very near the real world now. If I could just spare another couple of minutes, I'll just tell you something that we did about 2 months ago, actually. So this is very new. Near real world. Why I call it near real world is that we haven't actually considered the spatial variation, the 3x. And that was something that we did about 2-3 months ago, introducing spatial variation into this analysis. I like to show this picture because that for those of you who do not work in spatial data, you can just understand this using my picture. 1 and 2 represents 2 tests you conducted at the site, right? 1 test 2. The yellow dots represents the missing data, things that you don't do. So far I've been talking about cross correlation, basically correlation between 2 different test types, 1 and 2. Let's say between your cone test and your undrained shear strength, for example. I'm assuming that the correlation between information at 2 different depths is 0. In other words, all the records are independent. That's not quite true, because spatial variation, there will be a spatial correlation. And that was not considered. So if you look at music 3x, the key difference is that you have a correlation between 1 and 2, but the correlation between 1 and 2 is not perfect because they are not located in the same horizontal location or plane location. And so you need to consider horizontal correlation. And then if you at different depth, you need to consider vertical correlation. You can't put them as 0, it's too simplistic. So it's a matter of introducing this correlation into your analysis. It's quite difficult. So to put it all these things together in a very simple way, 1, 2, 3 represents 3 different test types. This will give you a sense of the kind of analysis we're working on. The yellow dots represents missing data, nothing at that depth. The red are the things that you measured, and they're all located in different locations, spatial location. I just drew a 2D, but actually it's 3D, right? The distribution. So if you all need to have a research topic, you want to solve something, then this will be the picture that you need to solve because we are here now. I don't think we solved it perfectly. We got somewhere, but I think we need more work, just to tell you the truth. So now it's multivariate, it's incomplete. So just very quickly, this is the last set of answers that we obtained recently. We took a site, it's not the largest, by the way, it's smaller than the Empire State Building, 25 by 15 meters. The depth direction is only 15 meters. that's not very deep, honestly, even for a foundation. But it's a real site in Texas, Baytown. Nothing special about Baytown, Texas. I don't even know where it is. You can go and Google. So it's a small little city somewhere in Texas. We happen to have this set of data. Very routine, in other words. So what we did now is that we have managed to create, we managed to do a simulation where we can actually simulate the changes in the depth direction. Even though you only have 3 data points. So these are the actual measurements, the yellow ones. And the red and the black and the pink represents the 95% confidence, depending on whether you want to use hierarchical Bayesian or you don't want to use hierarchical Bayesian. If you use hierarchical Bayesian method, you get a more narrow 95% confidence interval, even though you include a spatial variation. I think that's very nice. And of course, we can also do conditional random field simulation. That's quite difficult, by the way. I don't think I'm perfectly happy with it, but okay, it can be done. Number one, that's good. It shows that at least there's a solution. But more importantly, what we have now at this point in time, we got it down to a stage where it can be solved in a reasonable time for this particular 3D site. If the site were to get larger, let's say 50 by 100 meter, let's say 50 meters deep, right? That's a big site, that volume. I think we may not be able to solve it in a time frame that the engineers are willing to accept. So we're trying to push the boundary of computation as well. So that's our challenge, because if we can't do that, then forget it. Engineers are not going to use it. So I may have taken up too much time, but if I could, I just quickly give you all some observation of all the work that we've done for the past 3 years. We've been grappling with the issue of ugly data, which I told you is not the ugliest, it's just ugly. We only deal with 3 challenges on the site characterization problem. It's the simplest and it's also the most important problem at this point in time. The biggest challenge we are facing now is music 3x, especially the 3x part, we are struggling. The best answer we have now is this hierarchical Bayesian method, but I'm thinking that there has to be a better method out there. That's my belief, and we are now seeking for a better solution that can outperform HBM music 3x. In order for us to accelerate the progress in the whole field, we need to have benchmark examples. All right, so we have a standard set examples. This is very common in machine learning, by the way. So you develop your method, I develop my method using a common platform. We test it on the same example. In that way, I think methods that are not so efficient, we don't study them anymore, and then we all of us start attacking and improving methods that are more and more hopeful. I think this is very important. It has been very successful for the machine learning community, and just quickly to let you know, if you are interested, we have actually done benchmarking. I have no time to talk about it. I'll stop here. But the idea is that if you need it, we have benchmark examples. So we can send you the benchmark data as well for you to try. So I'll stop here, Francis. Thank you so much, everybody.
Thank you so much for your talk, Professor Phoon. That was really amazing. And thank you for giving us a really nice overview of your work for the past 3 years, kind of covering ugly data, site recognition, and stratification. I have a question just to get the ball rolling, and then we'll open up the floor to the audience to see whether they have any questions too. This might be a slightly naive question, but I really liked your, I thought it was hilarious, your idea of having this godsend data that we would all love to answer our research questions. I'm wondering whether you have any guidelines or tools to make sure that you're getting the best possible data in terms of kind of striving towards godsend data, or trying to maybe even have the data adaptable and suitable for your methodology. What guidelines could you propose for people to collect the data that's necessary?
Francis, so thanks a lot, right? Well, we're hoping, that's our ambition. Our ambition is that we can actually use any kind of data that the practitioner collects in the actual site. And then we should develop clever techniques to tell the practitioner whether his data is usable or not. I think it can be done. I think there are lots of clever people in our community. So that's been our objective. In fact, we actually collected, if you recall my presentation, we collected all these huge databases. These huge databases are very useful, I did mention. In fact, one of the main reason why we did it for the past 10 years is because this information are based on research studies. So they are going to be very reliable, number one. They are data we collect from the published literature, so they've gone through peer review. And number three, we ourselves have actually screened the information. We're hoping that if we offer this data to everybody, maybe with this data as a background, there's a way that we can actually check for the engineers whether their database is useful or not useful. It's not a black and white answer, but so that was just to set the foundation for your question, essentially.
Sorry, my mic's muted. Yeah, I appreciate it's quite a complex question with lots of nuance around what the purpose is and the specifics of a data set. But thank you, that's really nice.
So just very quickly, Francis, just to add in, that data is actually available publicly that you could download.
Sure. Okay.
Yeah, just to let all of you know.
Thank you. Adolphus, would you like to ask your question?
Yeah, sure. Thank you so much, Francis. Good evening, Professor Phoon. So once again, thank you so much for your insightful discussion. Although geotechnics isn't my pretty much the context of my research right now, but it's definitely very interesting to learn more about this topic through your presentation, which I really appreciate it. So thank you so much on that. I basically have two questions from our discussion this evening for you. So we'll go through question by question. My first, which probably a very simple clarification, just about quasi-site specific model. Just want to know, like, this quasi-site specific model, is it practically just a general form of a single model function, or is it basically consisting of a class of, like, models of different functional form?
Well, the way we visualize this is that we have we can use information that's available at your site, which is very limited. Hence, I showed you an example. We only have 3 data points. You can't construct any models using 3 data points, right? I mean, you're not going to get. It doesn't matter how clever you are. You end up with a huge amount of statistical uncertainty.
Yeah.
So when we look at quasi model, it just simply means that you have to rely on other sources of information. And so one example we use would be, in terms of other sources of information, would be other site information, other site investigation information. But then the problem you're going to face is that information from other site is not directly applicable to your site of interest because of geological differences. And so the research challenge now is to combine these databases with your site. As long as you consider the site differences, you don't combine in an indiscriminate way. We call this quasi-site specific models, because you do try to combine similar information together.
Right.
So that's how we define, and we are just very open about it. You don't have to think about combining site data with site data. You may be able to combine, let's say, site data at your site together with, let's say, load test data at another site, because load test data says something about your site as well, right? Maybe it could even be satellite information. So there's a whole bunch of things that we are quite excited. It can be any kind of data, by the way.
Sure.
So we hope to go in that direction.
Sure thing. Thank you so much, Professor. All right. So for the second question, basically, I noticed from the presentation that we are looking only in the case whereby you have all the you have considered only that one specific sub data. It could be incomplete or complete, and you are basically going to do the Bayesian inference from that. Now, I was considering because I'm currently working with online Bayesian inference, whereby you are looking at real-time updating, whereby you consider information coming in at different chunks of time. I was wondering, could this have we considered this online Bayesian framework into the geotechnics analysis, especially if you want to, let's say, consider the changes in the soil condition in real time, and whether is this feasible, considering now we have this thing called the Music 3x challenges that we just talked about.
Yeah, that's a great question, right? Because the way we think about it is that let's assume you have a tunneling problem and your tunneling machine is moving forward. And it's not possible that in a natural deposit, you have a situation where your tunneling is going through deposit that change every single meter or even every single centimeter. So there's a certain degree of persistence or correlation spatially. So the question that everyone is struggling with as an engineer now is basically the fact is that can you use the information that you collected when your tunneling machine went past? So these are actually time information. You could also say spatial information. So at what point in time can you actually rely on information you collected in the past stages of your project? So let's call it past stages. And then use that to inform your decision making going forward. And then at one point in time, are you starting to detect that the changes are coming? It's all the same. I think it's all under the same as this site recognition problem I'm posing. And this will be really valuable, let me tell you that. Just to let you know in terms of tunneling concept, because you know changes are coming, you're going to slow down the machine.
Yeah.
And because you have to be very careful. Whenever there are abrupt changes in a geologic condition, there's I can talk for an hour about that, but just understanding when the tunneling machine is going through similar soil, going through different soil, just that alone will be so valuable to a practitioner.
Interesting.
Yeah. So that the X can represent time and space variation.
Nice. All right. Yeah, but thank you so much for your clarifications and insights to our questions, and I'll leave others to their questions as well. Thank you so much, Professor.
Thanks a lot.
Thanks, Adolphus. Do we have any more questions from the audience?
I think Scott has one.
Oh, I believe Scott just messaged something. Sorry, go ahead, Scott.
I'm nervous. I seem to have a bad connection, but in case you can't hear me, I put it on the chat. But it says about that C in the music acronym. Do you have any ideas about how you're going to approach corrupt data? And secondly, when you say corrupt data, are you talking about just bad sensors and transmission errors, such as I might get on my bad Zoom call, or are you talking about actual lying, like Karen Silkwood, and the misreported data, or the pandemic numbers that maybe come from Florida that we don't really trust?
Great question, Scott. Actually, we have no clue. We haven't actually attacked this problem seriously. But just to let you know, this is not a hypothetical problem. In our profession, we have people actually cooking up data. So they never do the test at the site. They just cook it and they fill in the table with numbers that they think is correct. So this is not uncommon. It's not like something that invent. We also have the less serious problem that you mentioned, where the just using the cone test that I just showed you, that nice machine in Finland. We have cases whereby the test was not run correctly, because you need to do certain things right. In this particular cone test, you actually need to have one part of the test has to be fully saturated. You have to make sure that the test is fully saturated in order to measure the pore pressure correctly. And it's very common that people don't do it correctly. So sometimes you see all this variation. You don't even know whether the variation is real. It can be real, by the way, because you encounter different soil types, right? Different soil types create different pore pressure response. Or it could be that the test was incorrect because you didn't do the test correctly. So the sources of this corruption happens. Engineers do struggle with it. The way we look at bad data at this point in time is just a practical definition that if there's a way we can reduce them or get rid of them in a systematic way, then of course that'll be wonderful. Because clearly if you incorporate all this information into analysis, right, you can end up with a wrong answer because it's wrong data, wrong answer. But we got no clue how to do this easily at this point in time, honestly. Other than to know that if we are going to go into this space that I was telling Francis, right, we're not going to, for the past 10 years, we've been staying in this very safe zone. We work on research data. These are done by really, people experts in this field doing meticulous tests. We've collected the database. I think the amount of bad data in our database is almost minuscule. I have great faith in it. We are not going to step into that brave world where we're going to go into the industry, use the industry data. That would be the challenge, Scott. Why we need to think about the sea. I think it is not a minuscule. This is a corrupted data. If you want to use industry practitioners' data, so that's the motivation. I don't have an answer to your question though.
Well, yeah, I don't think that anybody does. But thanks very much. That's really useful. The X and the 3X. Why did you say 3X, not 3D? I'm just curious.
Say that again.
Well, you said music 3X. Why is it X instead of like just 3D or just 3 maybe? I was confused by that at the time.
Oh, we just wanted to call it X because it's like we wanted to indicate it's a spatial dimension. So X is like X coordinate.
Okay.
So it's like X1, X2, X3.
Oh, that makes sense.
Right, of course. Well,
because 3D could refer to many things.
Sure. Okay. Well, thanks very much. It was a great talk. I really, it made me laugh out loud when you said it's uglier. No offense.
Well, it is. Yeah, I have to be a very moderate nowadays.
Right. And the other thing that made me laugh out loud is that you called the ugly data. The definition of ugly data is the data that you have.
It's quite funny, Scott, because I learned that from your presentation in Hanover that since all of us agree that deterministic data is the one that we all pine for, so I decided that let's call deterministic data the prettiest girl in the ballroom maybe. And I say, why not, right? All of us are, you work on all this imprecise information. And I said, why don't we just call our data ugly?
Right.
We're the ugly blokes. So I thought that's fine.
Thanks very much.
What an analogy.
Do we have any more questions from the audience? And if not, I was going to ride on the back of that and question whether the data that you find in papers when they give deterministic data, and you say that you go through the literature and you might use values in the literature that are peer reviewed, is it possible to trust those values implicitly? Because at least in the field that I work in, which isn't geotechnics, but in indoor agriculture, a lot of the values have been peer reviewed, but they're deterministic, and I don't think they're particularly reliable because every farm and an indoor environment is so different with different microclimates within the farm that I found a lot of errors when you try and check or proof check those values. And I'm wondering whether maybe, I presume in geotechnics and in civil engineering, it's a lot more robust, it's a lot more of an older field. But long story short, do you trust the data implicitly that's been peer reviewed, or do you have a way of checking to make sure that it's actually correct, and whether you're skeptical at any point?
Yeah, that's a good question, Francis. It's a fair question. In fact, just to answer it in a very short way, yeah, we're very skeptical. When we talk about us trusting the data, it wasn't that we trust it because it was peer reviewed and we took it from,
of course,
papers written by famous professors. Just to let you know that we took the data, and this data came from all these sources that are basically from research studies. And then what we did was that we ran it through every single test we could. And it's not statistical test alone, Francis. We ran it through physical tests.
Yeah.
So we put it through a huge screening process before we accept those data to be kind of like data that we trust. And in between while we're doing that, we found things that are not. We found stuff that we should leave it out. So when we did our database compilation, it wasn't a case of us just compiling data, raw data from all the papers.
Okay. Yeah, it goes.
So it's been scrubbed, like it's been scrubbed, and hence when I encourage people to download our data, if you want to play with it, I want to give you all the assurance that it's gone through the best that we could to detect information that if you use those information, it's not going to help our research at all. So we are very cautious. And in fact, we're very skeptical. I wouldn't guarantee it's perfect. That 7,000 odd data set I told you, I can't guarantee everything is going to be good. But I'm almost certain that you're not talking about even 10% bad. I don't know, maybe a couple of pieces are bad.
Yeah.
But it's going to be 99.9% good. So good enough for us to work in.
Okay, fantastic. All right, thank you very much. Are there any more questions in the audience before we wrap up? If not, I'd like to thank our speaker again. And it was just fantastic to learn a little bit more about your field and your discipline. Thanks so much for your time and your effort putting together this presentation. I really enjoyed it. I'm sure I speak on behalf of all of us who enjoyed it as well. I think for those that weren't able to attend the talk, would you be able to tell us again where people can find out more about your work, whether they can visit a website or the paper that you said that people can review that gave an overview of your presentation today?
Yeah, so anybody who is interested, I'll be happy to, you could contact me by email. Yeah, whatever information you could need, just feel free. I thought, you know, the problems are really complex. And I think there are similarities in some of the works that you are doing as well. So I really think you all should be sharing smart ideas with me, and maybe we can even work together, right? Because this is essentially data analysis. So yeah, I mean, feel free to contact me. I'm very eager to see whether we can get better solutions out of this. I think we can, and then we'll get all the engineers excited. And you know, to me, I think that's how we shift from this a deterministic paradigm to the real world, I guess. So yes, feel free to contact me. Thanks.
Okay, fantastic. Thanks again for your talk and for staying up and working in the evening to give us this talk. And all the best, and hope to see you in person at some point in the future.
Yeah, thank you very much, Francis. I hope to see you and Scott as well. Thank you so much for having me.
All right, thank you.
All right, bye-bye.
See you later. Have a lovely evening.
Yep.
Bye.
Bye, you too. Bye.